Tonight, under the vast dome of the American sky, we turn our gaze outward beyond the planets, beyond the reach of the sun, into the deep and endless dark where stars are born and worlds are lost. In that infinite ocean of space, a traveler once crossed our path. It came silently, without warning, glowing faintly as it drifted past the orbits of Mars and Earth. Astronomers named it 3I Atlas, the third confirmed visitor from another star system. But from the moment NASA detected it, something about this object didn't fit. It moved differently, it broke apart strangely, and its composition whispered of places no human eyes had ever seen. This is not just a story about a comet. It is the story of a mystery that reached across light years to challenge everything we thought we knew about how the universe works. For months, scientists at NASA worked around the clock measuring, observing, questioning until, finally, they confirmed what 3I Atlas truly was. Their discovery did not close a chapter in astronomy. It opened an entirely new one, reshaping how we think about interstellar space, and perhaps, about our place within it. Long before NASA officially confirmed the nature of 3I Atlas, our collective curiosity had already been primed by two extraordinary guests from beyond the solar system. The first was Oumuamua, detected in 2017, and the second was Borisov, discovered in 2019. These cosmic wanderers weren't just fascinating, they completely redefined how we think about our place in the galaxy. When astronomers first spotted Oumuamua streaking through the inner solar system, it appeared unlike anything we had ever seen. It wasn't orbiting the sun in the way asteroids or comets typically do. Its hyperbolic trajectory meant it wasn't bound by our sun's gravity. It was simply passing through, on its way from one corner of the galaxy to another. The discovery marked the first time in history that humanity had confirmed an interstellar object, a visitor from another star system crossing through our own. First, scientists were unsure what to make of Oumuamua. It didn't emit a visible coma like a comet should, and it reflected sunlight in strange, inconsistent ways. It was long, narrow, and tumbled end over end as it moved. Some researchers even compared its shape to that of a cigar or a pancake, depending on the light curves they analyzed. The more they studied it, the stranger it became. It accelerated slightly as it left the sun's influence, behavior that could be explained by sublimating gases if it were a comet, but no visible signs of such gases were ever detected. This small acceleration became one of the most puzzling aspects of Oumuamua's story, sparking speculation that ranged from natural explanations, such as hydrogen outgassing or dust-driven jets, to more unconventional ideas, such as it being an artificial probe, perhaps a relic of alien technology. 2 years later, another interstellar traveler entered our skies, but this one was less mysterious in behavior and more familiar in composition. Discovered by amateur astronomer Gennady Borisov in 2019, the comet, later named 2 Borisov, was immediately recognized as interstellar in origin. Its velocity and trajectory told scientists that it, too, came from outside the solar system, likely from the vast spaces between stars. Unlike Oumuamua, Borisov looked more like a traditional comet, complete with a bright coma and a dusty tail streaming behind it. Its composition contained water, carbon monoxide, and complex organic molecules, similar to those found in comets that formed around our own sun. The discovery of Borisov reassured scientists that not all interstellar visitors had to be enigmatic or unexplainable. Some could be natural remnants of planetary systems that formed and disintegrated long ago, ejected into space during the violent early stages of their home system's evolution. These two discoveries set the stage for the story of 3I Atlas. They opened a new chapter in the field of interstellar astronomy, proving that our solar system isn't an isolated island in the galaxy, it's part of a vast network of star systems that share material across unimaginable distances. Each interstellar object that passes through offers us a fleeting glimpse into the chemistry and physics of other planetary systems, snapshots frozen in motion as they travel through the void. When Oumuamua appeared, it was the first sign that such visitors existed. When Borisov followed, It confirmed that these events might not be as rare as once believed. And so, when astronomers detected yet another strange, fast-moving body, one they would later call 3I Atlas, they knew it could represent something extraordinary. The story of 3I Atlas begins with this lineage, this quiet but powerful realization that the universe is not static. It moves, it trades, it exchanges fragments of itself. Each interstellar object carries the signature of its origin, an alien fingerprint written in dust and ice. For scientists at NASA, the excitement wasn't just in identifying these visitors, but in understanding what they meant. Each discovery challenged the boundaries of planetary science, forcing us to question what we thought we knew about formation, stability, and migration in the galaxy. Oumuamua's strangeness taught us that the galaxy could throw surprises our way, objects that didn't conform to any known category. Borisov's familiar behavior reminded us that, for all our technology and advanced telescopes, we were still witnessing basic, universal processes, the creation and destruction of icy bodies born in the chaos of young stars. When these two discoveries were analyzed side by side, they gave NASA and the global scientific community a framework for identifying new interstellar objects. Astronomers began refining detection systems, building better sky surveys, and programming telescopes to automatically flag fast-moving bodies on hyperbolic paths. That work paid off. In late 2024, data from NASA's collaborations with the Atlas Asteroid Terrestrial Impact Last Alert System survey revealed an unusual point of light moving rapidly across the background of distant stars. At first glance, it resembled a faint comet, but its velocity and inbound trajectory didn't fit any known pattern for solar system comets. As early observations trickled in, it became clear that this was no ordinary object. Scientists realized they might be witnessing a third confirmed interstellar visitor, a new piece of the cosmic puzzle that Oumuamua and Borisov had begun. But before NASA made any official statements, they approached the data with caution. The history of Oumuamua's controversial interpretations taught researchers to tread carefully. They began comparing 3I Atlas's movement, brightness, and light spectrum with that of its predecessors. Early results revealed subtle similarities with Borisov. There were traces of a possible coma, suggesting some level of volatile activity, but there were also elements that didn't match any known cometary signature. Its brightness fluctuated unpredictably, and its dust production seemed inconsistent, fading rapidly at times, and then reappearing. For the public, the discovery of another interstellar object sparked renewed fascination with what lies beyond. For scientists, it was a chance to refine models and theories that had been built on sparse data. Each of these visitors, from Oumuamua to Borisov to 3I Atlas, provided just fragments of understanding, like pages torn from a cosmic encyclopedia scattered across light years. And yet, those fragments were enough to piece together a broader narrative of how material travels across the galaxy. The story of Oumuamua had ended with more questions than answers. The story of Borisov had offered a sense of reassurance, proof that natural interstellar comets existed. Now, with 3I Atlas, NASA hoped to find balance between those extremes, to learn whether this new object would follow the predictable patterns of Borisov or challenge expectations like Oumuamua did. When astronomers looked back at those earlier discoveries, they realized that they had unknowingly set the groundwork for a new field of study: interstellar object research. The emotional resonance of these discoveries was profound. For many astronomers, Oumuamua was a reminder of how much we still don't know about the universe. For the general public, it was a moment of awe, a chance to dream about distant civilizations, and the possibility that our solar system might not be so alone. For NASA, it was a call to prepare to improve detection systems, to ready future missions that could one day intercept such visitors and study them up close. Borisov's passage, on the other hand, gave scientists comfort. It was proof that interstellar objects could be studied using familiar methods. They could be observed, measured, and categorized. But even that sense of familiarity carried with it a subtle wonder. The idea that comets forming around distant suns might not be so different from our own. that the chemistry of life could be scattered across the galaxy in frozen fragments, traveling from one system to another. So, when 3I Atlas was detected, the excitement wasn't just about confirming its origin. It was about connection, about being part of a story that stretched across time and light years, linking three objects that had crossed our skies in just one human generation. From the moment Oumuamua flashed across telescopes to the steady glow of Borisov, and now the strange pulse of 3I Atlas, we've been watching a new cosmic pattern unfold, one that reminds us how fluid the boundaries of our solar system truly are. NASA's journey toward understanding what 3I Atlas really is begins here, with memory, with history, and with the lessons learned from the first two interstellar visitors that captured humanity's imagination. Each arrival reshaped our expectations, each departure left us with deeper questions, and each new discovery pushed the limits of how far our scientific curiosity could reach. The story of 3I Atlas doesn't exist in isolation, it is part of a continuum that began the moment we realized the universe sends us messages in the form of travelers from the stars. The story of 3I Atlas began quietly, without fanfare or the dazzling headlines that would come later. In the stillness of the early morning sky, deep within the data streams flowing from the asteroid terrestrial impact last alert system, or ATLAS, something unusual began to take shape. The ATLAS survey, a network of telescopes stationed across Hawaii and other strategic observation points, was designed to spot potential threats, asteroids that could cross paths with Earth. It was never built with the intention of finding messengers from beyond the solar system. Yet, like so many great scientific discoveries, this one came as a result of curiosity and precision meeting chance. In late 2024, astronomers monitoring the Atlas sky maps noticed a faint, fast-moving object that didn't fit with any known catalog body. The automated detection software flagged it as a possible near-Earth comet, but when researchers began to trace its movement across multiple nights, something didn't add up. Its speed was extraordinary, far exceeding the typical velocity of an ordinary comet bound by the sun's gravity. Moreover, its trajectory when projected backward didn't seem to loop around the sun in a conventional orbit. Instead, it was traveling along a hyperbolic path, an open curve that indicated a one-time passage through our solar system, never to return. The data soon reached NASA's Center for Near-Earth Object Studies, where astronomers double-checked the numbers. Within days, it became clear this wasn't an ordinary discovery. The team realized they might be looking at only the third confirmed interstellar object ever observed, an object whose origins lay beyond the gravitational influence of our Sun. The provisional designation, C2024A3 Atlas, would soon be replaced by something more significant, 3I Atlas, marking it as the third interstellar object ever identified, after Oumuamua and Borisov. From the very beginning, 3I Atlas displayed an intriguing duality. On one hand, it behaved like a comet. There were signs of a coma, a faint cloud of vaporized gases surrounding its nucleus as sunlight began to heat its surface. On the other hand, its structure and reflectivity suggested it wasn't typical. The spectral data gathered from ground-based telescopes showed inconsistencies in its composition. Some regions of the object reflected sunlight strongly, while others absorbed it almost entirely. Its light curve fluctuated, implying that the object was rotating irregularly or that its surface was unevenly shaped. Astronomers had seen something like this before. Oumuamua, the first interstellar visitor, had also demonstrated an erratic brightness pattern that hinted at an elongated shape. But where Oumuamua lacked any visible tail or outgassing, 3I Atlas displayed faint signs of activity, something akin to what you would expect from a volatile, rich comet venting material as it approached the sun. This immediately set it apart. Borisov, the second interstellar object, had been a textbook comet, icy, dusty, and visibly active. 3. Atlas seemed to exist somewhere in between, behaving like a comet but defying the standard expectations of one. When news of the discovery reached the public, excitement rippled through the astronomy community. Telescopes around the world pivoted to capture it. The European Southern Observatory, the Hubble Space Telescope, and numerous ground-based observatories began coordinated efforts to study the object before it faded from view. Each observation was a race against time. Because interstellar objects move at incredible speeds, tens of kilometers per second relative to the Sun, they spend only a brief window of time close enough for detailed study. Every day counted. NASA scientists noted that 3I Atlas was traveling faster than 50 kilometers per second. Its velocity so great that no gravitational force within the solar system could ever capture it. Its inbound path suggested it came from a direction near the constellation Hercules, a region rich in older stars and ancient stellar debris. Tracing its trajectory backward, astronomers theorize that it could have originated from a distant system hundreds of light years away, possibly ejected during the chaotic early days of a forming planetary system. In such scenarios, gravitational interactions between nascent planets can fling smaller bodies, comets, asteroids, icy fragments into interstellar space, turning them into cosmic wanderers destined to drift through the galaxy indefinitely. For the scientists analyzing 3I Atlas, every piece of data mattered. Using spectroscopy, they attempted to decode the object's chemical fingerprint. The spectra hinted at the presence of water ice and carbon-based compounds, but there were also puzzling features: emission lines that didn't correspond neatly to any known cometary material. Some suggested the presence of exotic ices, like ammonia hydrates or carbon dioxide frost, which would imply that 3I Atlas formed in an environment much colder than our solar system's outer reaches. Others speculated it might contain materials altered by cosmic radiation over millions of years drifting through interstellar space. One of the most intriguing aspects of 3I Atlas's discovery was how quickly it challenged assumptions. With Oumuamua, astronomers had been cautious but fascinated by its unusual shape and unexplained acceleration. With Borisov, they had confirmed that interstellar comets could exist and could be studied with traditional cometary models. But 3I Atlas seemed to blend both phenomena. It behaved like a comet, but didn't fully obey the rules of one. Its tail, for instance, didn't appear to align perfectly opposite the Sun as expected. Instead, it showed a subtle deviation, as though its dust and gases were being influenced by something more complex than solar radiation pressure alone. NASA's early mission planners and theorists took note. If this object was indeed the third interstellar visitor, it could provide vital data for future missions aimed at intercepting such travelers. In fact, the discovery of 3I Atlas reignited discussions about launching fast-response spacecraft capable of studying interstellar visitors in real time. After all, each of these objects carried within it a sample of material from other star systems, a natural interstellar probe arriving at our doorstep. For planetary scientists, that was an irresistible opportunity to study the chemistry and structure of alien worlds without leaving our own. The process of confirming 3I Atlas's interstellar status involved meticulous calculations. Astronomers had to measure its eccentricity, a value that determines whether an orbit is closed or open. Anything greater than 1.0 meant the object was on a hyperbolic trajectory. For 3I Atlas, the eccentricity measured well above that threshold, confirming it was not gravitationally bound to the Sun. In other words, it came from the stars and would return to them once its brief encounter with our solar system was over. As scientists analyzed its motion, they noticed another fascinating detail. 3I Atlas was entering the solar system at an unusually steep angle relative to the plane of the ecliptic, the flat, disc-shaped region where most planets orbit. This suggested that its path through space had been largely unaltered by interactions with other stellar systems, meaning it had likely been traveling undisturbed for millions of years. It was a pristine relic, carrying unmodified clues about the conditions of its birth environment. To visualize it was to imagine a cosmic messenger gliding silently into our celestial neighborhood, illuminated by sunlight for just a moment in its endless journey. The very idea that a small object, possibly no larger than a mountain, could travel across interstellar space and be detected by human instruments spoke to the remarkable reach of modern astronomy. For NASA scientists, 3I Atlas represented both a scientific mystery and a philosophical reflection, a reminder of how interconnected the universe truly is. Amid the analysis and excitement, debates began to stir. Some argued that 3I Atlas was simply another interstellar comet, an icy fragment carrying the signatures of a distant sun. Others, intrigued by its irregular light patterns and inconsistent dust emissions, wondered whether it might represent an entirely new class of objects, bodies that blur the line between comets, asteroids, and something else entirely. NASA scientists approached the question carefully, aware of the public fascination that surrounded Oumuamua's unconventional theories. This time, they wanted to ensure the evidence spoke clearly before speculation took over. Meanwhile, amateur astronomers around the world pointed their telescopes skyward, hoping to catch a glimpse of the visitor before it faded from view. Images began circulating online, faint, grainy streaks across dark skies, reminders that even with all our technology, these fleeting cosmic guests remained elusive. 3I Atlas was moving quickly, its brightness fluctuating as it reflected sunlight from its uneven surface. By the time it reached perihelion, the point closest to the sun, it was briefly visible through mid-range telescopes before beginning its long exit into the outer darkness. For NASA's astronomers, the discovery of 3I Atlas was more than just another data point. It was an event that confirmed how much the universe still had to teach us. It demonstrated that interstellar visitors might be more common than we once thought, perhaps drifting through our solar system every few decades, unnoticed or misidentified. Each one was a messenger from the unknown, carrying fragments of the story of other worlds. 3I Atlas, like its predecessors, had entered our skies as a faint signal from the edge of the galaxy, a whisper that science could translate into understanding. And for a brief time, before it slipped back into the infinite dark, it offered humanity a glimpse of what lies beyond our solar home. When NASA's team officially classified 3I Atlas as the third confirmed interstellar object, the initial reaction across the scientific community was one of both excitement and deep caution. They had seen this before with Oumuamua, a discovery that began with fascination and quickly turned into a complex web of questions that data alone struggled to answer. This time, NASA wanted to move carefully. Every detail mattered. Every data point would be studied, cross-checked, and reanalyzed. The difference was that in 2024, technology and computational modeling had evolved significantly since 2017, allowing scientists to examine 3I Atlas with greater precision. Yet, even with all those advancements, the data that came back did not fit neatly into the familiar templates of comets or asteroids. The first round of observations focused on determining the object's structure and activity. Using NASA's NEOWISE telescope and data from the Hubble Space Telescope, astronomers began studying 3I Atlas's reflectivity and light curve. What they found was immediately perplexing. The object's brightness fluctuated in ways that suggested it was rotating irregularly, perhaps tumbling through space, much like Oumuamua had. However, unlike Oumuamua, which showed no visible sign of outgassing, 3I Atlas appeared to have a faint but detectable coma, an envelope of gas and dust surrounding its nucleus. Normally, this would classify it as a comet. But here's where the data began to deviate from expectation. The composition of the coma didn't resemble that of typical comets. NASA's infrared instruments detected a surprising lack of carbon monoxide and carbon dioxide, gases commonly released when comets heat up near the sun. Instead, there were traces of unidentified volatile compounds, molecules that didn't correspond to any known pattern observed in solar system comets. The presence of such materials raised a fundamental question. What kind of environment could produce such chemistry? If 3I Atlas originated from another star system, perhaps it formed under conditions completely foreign to our solar system, maybe around a dim red dwarf star, or in the outer fringes of a distant system where exotic ices condensed in extreme cold. As the data accumulated, researchers began comparing 3I Atlas's readings with those from Oumuamua and Borisov. Oumuamua had been dry, with no visible gases, while Borisov was rich in water and carbon-based compounds. 3I Atlas fell somewhere in the middle, behaving inconsistently. Sometimes it looked like a comet, faintly shedding dust. At other times, it appeared inert and stable, like an asteroid. This irregularity confused scientists. A comet's outgassing typically increases steadily as it approaches the Sun, yet 3I Atlas's activity seemed to flicker unpredictably. NASA's early hypothesis was that the surface might be patchy, some regions covered with volatile ice capable of sublimating under sunlight, while others were coated in darker, inert material that absorbed heat but didn't vent gases. But the more they studied it, the stranger it became. NASA's Deep Space Network detected minute but measurable changes in the object's velocity that couldn't be fully explained by gravitational forces alone. It was subtle, just a small deviation from the expected trajectory, but enough to raise questions. Could these shifts be caused by uneven gas jets pushing the object slightly off course, as with a normal comet? Possibly. Yet the direction and magnitude of the deviations didn't always match that theory. In some models, the acceleration seemed too uniform, as if it were being influenced by pressure from sunlight reflecting off its surface, or by internal processes we didn't yet understand. Scientists began exploring these anomalies from multiple angles. At NASA's Goddard Space Flight Center, teams used high-resolution modeling to reconstruct how 3I Atlas might have formed, incorporating its brightness variations and unusual composition into simulated environments. The results hinted that the object's surface might be composed of complex layers, outer crusts of radiation-darkened material overlying pockets of volatile ice. Over time, as it journeyed through interstellar space, cosmic rays could have altered its chemistry, breaking apart molecules and creating new compounds that no longer behaved like familiar cometary ices. That process, known as space weathering, could explain why 3I Atlas didn't release the same gases as ordinary comets even when heated. Adding to the mystery, spectral analysis revealed metallic elements in trace quantities, signatures of nickel and iron particles embedded within the dust. This was not typical of small icy bodies. It suggested that 3I Atlas might have formed in a region where rocky and icy materials mixed together, perhaps near the boundary between an inner rocky zone and an outer icy zone in its original solar system. If so, it might represent a hybrid type of body, part rock, part ice, something that blurs the distinction between comet and asteroid. Such a discovery would expand the classification of small celestial bodies, proving that interstellar space carries a broader diversity of material than previously thought. As NASA's teams continued to gather data, the conversation around 3I Atlas became increasingly nuanced. The first question was whether its observed properties could be entirely natural. Most scientists agreed that it was. Still, its behavior was peculiar enough to require rethinking how we define and model interstellar debris. If a comet can behave inconsistently, and an asteroid can exhibit slight activity, maybe these categories were never as distinct as once assumed. The boundaries between them might be fluid, depending on the object's history and environment. Another strange feature noted early on was the color of its surface. Observations in the visible and near-infrared bands showed that 3I Atlas reflected sunlight with a reddish hue similar to the colors seen on distant Kuiper belt objects like Arrokoth. This red tint is often caused by complex organic compounds called tholins, formed when ultraviolet light and cosmic rays interact with simple ices over long timescales. The presence of such material implied that 3I Atlas had spent millions, perhaps billions, of years, drifting through interstellar space, exposed to the radiation that slowly transformed its surface chemistry. It was, in essence, a fossil from another world, preserved in the cold vacuum between stars. Despite this progress, there were still more questions than answers. NASA's Jet Propulsion Laboratory modeled the object's spin and shape based on its light curve. The analysis suggested it was irregular, possibly elongated like Oumuamua, or even shaped like a loosely bound cluster of fragments held together by gravity. If the latter were true, 3I Atlas might not be a single solid body at all, but a conglomerate of smaller pieces that had once been part of a larger parent object. This theory gained traction when some astronomers noticed rapid fluctuations in its brightness that could indicate fragment shedding or surface cracking. Such behavior is not uncommon among comets nearing the Sun, but in this case, the timing didn't align perfectly with thermal expectations. Something else seemed to be influencing its activity, though no clear explanation emerged. To get a better look, NASA coordinated with the James Webb Space Telescope for mid-infrared observations. Webb's data provided unprecedented detail about the object's heat distribution, confirming that its temperature varied dramatically across its surface. Some areas were warmer than expected, while others remained surprisingly cold, even under direct sunlight. This uneven heating could support the theory of a heterogeneous surface, one covered with insulating materials that delayed heat transfer. It also suggested that 3I Atlas might have internal cavities or porous regions, capable of storing volatile gases that escaped in short bursts rather than continuous streams. Public curiosity about 3I Atlas grew as NASA released preliminary findings. Many wondered whether it could be artificial, as had been speculated about Oumuamua. NASA scientists, however, remained grounded in the data. They explained that while some of its characteristics were unusual, all could still be explained by natural processes within the realm of astrophysics. The idea of an artificial origin, though fascinating to many, lacks supporting evidence. Instead, the focus was on understanding what made this object's chemistry and behavior so distinctive. If it wasn't a comet or asteroid by traditional definition, then perhaps it was something entirely new, a transitional object that broadened the boundaries of planetary science. In scientific journals, papers began emerging that proposed new models for 3I Atlas's formation. Some suggested that it might have been ejected from a binary star system, where gravitational interactions could create stronger forces that accelerate debris into interstellar space. Others speculated it might have originated from the outer edge of a young, volatile-rich planetary disk, regions so cold that exotic ices could condense. These scenarios fit with the chemical anomalies observed in its spectrum. NASA's teams leaned toward the idea that 3I Atlas was a relic of such a cold, distant system, one where elements like ammonia and methane could freeze solid and survive the ejection into space. As the weeks passed and 3I Atlas continued its trajectory outward, the chance for direct observation began to diminish. The faint signal it reflected back to Earth grew weaker, leaving NASA with only the data already collected. What remained was an archive of spectral lines, photometric readings, and trajectory plots enough to occupy researchers for years. Yet even in that limited window of observation, 3I Atlas had already proven itself extraordinary. It was the kind of discovery that forced scientists to question long-standing assumptions, to reconsider definitions, and to expand models of what interstellar debris could be. Through those early investigations, one truth became clear: 3I Atlas did not fit the mold. It wasn't just a comet passing through or an asteroid that had lost its way. It was something more complex, a body shaped by cosmic forces we were only beginning to understand. A visitor whose data whispered of distant suns and alien processes that had unfolded far beyond our reach. For NASA, this was exactly the kind of mystery that makes science worth pursuing. A reminder that even in the age of advanced telescopes and artificial intelligence, the universe still holds its secrets just out of reach, waiting for us to look a little closer. When NASA's team began analyzing the trajectory of 3I Atlas, they knew from the very beginning that the path of this object would hold the key to its true origin. In celestial mechanics, an orbit tells a story, a record of the forces that have shaped an object's journey across the cosmos. Every curve, every deviation, every tiny adjustment in its speed reflects something about where it came from and what it encountered along the way. For 3I Atlas, that story was written in a language of numbers and vectors, but its meaning reached far beyond mathematics. It spoke of a journey that began light years away, a journey that carried fragments of another star's world into the realm of our own. To trace its path, astronomers at NASA and across the world used an intricate combination of optical tracking, radar modeling, and orbital simulation. By collecting positional data over several weeks, they were able to plot its motion relative to the Sun, the planets, and the galactic background. The first thing they confirmed was that 3I Atlas was not bound to the solar system. Its orbital eccentricity was well above 1.0, a clear indicator of a hyperbolic trajectory. That meant it had come from interstellar space, and would leave the same way its visit to our solar neighborhood would be brief and unrepeatable. But just knowing that it was interstellar wasn't enough. NASA's scientists wanted to know where it came from. Every interstellar object carries within its path a subtle hint of directionality. By tracing 3I Atlas's trajectory backward, before it entered the solar system's gravitational influence, researchers could estimate the region of space it might have originated from. Early calculations pointed toward the general direction of the constellation Hercules, though the uncertainty was vast, spanning many light years. The region contained numerous stars, including several red dwarfs and older stellar remnants. These stars, some billions of years old, were surrounded by ancient debris fields, the remnants of long-lost planetary systems. It was from such a place, scientists theorized, that 3I Atlas might have begun its voyage. The concept of ejection is central to understanding interstellar objects. In the early stages of planetary system formation, young stars are surrounded by protoplanetary disks composed of dust, ice, and rock. Over time, gravity causes these materials to clump together, forming planetesimals and eventually planets. However, this process is chaotic. Gravitational interactions between emerging planets can sling smaller bodies out of the system entirely, propelling them into interstellar space at immense speeds. Some of these ejected fragments, depending on their trajectory, drift quietly between the stars for eons until they are captured, if only momentarily, by another star's gravity. That is what scientists believe happened with 3I Atlas. NASA's simulations suggested that 3I Atlas could have been ejected billions of years ago from a system not unlike our own. Its velocity, measured at over 50 kilometers per second relative to the Sun, was consistent with the escape speeds expected from dense planetary systems where giant planets interact strongly. Jupiter-like worlds are particularly efficient at ejecting smaller bodies. In fact, theoretical models predict that for every planet that forms in a star system, thousands of smaller icy bodies may be thrown into the galaxy. These become the raw material of interstellar space, the seeds of discovery, when they pass near other stars. 3I Atlas, by this logic, was one of these castaways. Wander aimlessly until gravity brought it briefly within our observational reach. Tracking its motion beyond the Sun revealed more than just its velocity. As it curved around the inner solar system, the combined gravitational pull of the Sun, Jupiter, and Saturn subtly altered its course, allowing scientists to map its post-encounter trajectory with precision. When the data was extrapolated forward, NASA predicted that 3I Atlas would exit the solar system toward the constellation Lyra, moving into the northern galactic plane. In the vast scale of the cosmos, this direction meant little. It would travel for tens of thousands of years before coming close to another star, but for scientists, every detail helped refine models of galactic dynamics. One of the most fascinating insights from this tracking work was the realization that interstellar objects like 3I Atlas could serve as natural probes of galactic evolution. By studying their motion, scientists could infer the gravitational influences that shaped their paths, subtle tugs from stars, gas clouds, and the Milky Way's own spiral arms. Each object was like a tiny test particle drifting through the galaxy's vast gravitational field, recording its structure in slow motion. For NASA's astrophysicists, analyzing 3I Atlas wasn't just about understanding a single object. It was about using it as a data point to better comprehend how matter circulates through the Milky Way. As NASA refined the orbital data, they noticed a curious aspect of its inbound trajectory. Unlike the previous interstellar visitors, which entered the solar system relatively close to the ecliptic plane, 3I Atlas approached from a steep inclination nearly 60 degrees above the planetary plane. This meant that its motion was highly unusual compared to the majority of objects within our system. Such a steep angle supported the theory that it had not interacted significantly with other star systems during its long journey. It was, in many ways, pristine, untouched, unaltered, and representative of its original environment. This was scientifically invaluable. The pristine nature of 3I Atlas also gave clues about its interstellar exposure. Over millions of years, an object traveling between stars is bombarded by cosmic rays, micrometeor impacts, and interstellar dust. These interactions gradually erode the surface, darkening it and altering its reflectivity. NASA's analysis of its spectral signature showed evidence of this weathering, an outer crust coated in complex organic residues and carbon compounds. This surface layer acted like a shield, preserving the inner materials beneath it. It was a cosmic time capsule, one that had recorded the chemistry of a different solar system long before ours even existed. The more NASA's team studied the trajectory, the clearer the timeline of 3I Atlas's journey became. Its speed and direction through the local standard of rest, the average motion of nearby stars, indicated it wasn't part of any known stellar stream or moving group. In other words, it didn't appear to have come from a nearby star that we could identify. It was truly an independent traveler, perhaps ejected from a system that no longer even existed. Some scientists speculated that it might have originated from a system that underwent catastrophic change, perhaps a dying star or a region destabilized by a supernova shockwave. Events like that can fling debris across light years, scattering remnants of planets and comets throughout interstellar space. NASA's orbit reconstruction models also provided valuable insights into how often such visitors might appear. Based on the detections of Oumuamua in 2017, Borisov in 2019, and now 3I Atlas, astronomers began to estimate that interstellar objects could pass through the solar system roughly once every few years. Most go unnoticed, too small or too dim to detect, but surveys like Atlas and Pan-STARRS are making it increasingly likely that we'll find more of them. Each new discovery adds depth to our understanding of how material moves between the stars, and in turn, how planetary systems like ours evolve and exchange their ingredients across the galaxy. Tracking 3I Atlas also highlighted the incredible coordination between global observatories. NASA's data was combined with inputs from the European Southern Observatory, the Canada-France-Hawaii Telescope, and other institutions around the world. Together, these networks created a continuous stream of data that allowed precise measurement of the object's position across time. This collaboration turned 3I Atlas into one of the most thoroughly observed interstellar visitors in history. Every night, as it drifted further from the sun, telescopes captured its fading light, converting those faint photons into mathematical coordinates that revealed more about its origin and future. For the scientists involved, there was a quiet poetry in this process. Here was an object that had traveled for perhaps 1 billion years across the endless darkness of interstellar space, now briefly intersecting the orbit of a small, blue planet whose inhabitants had the technology to notice it. That encounter, fleeting, silent, and almost accidental, was enough to bridge two worlds separated by light years. The trajectory maps became more than just scientific documents. They were testimonies to cosmic connection, records of the moments when paths crossed between distant origins and human awareness. The physical modeling of its path also provided data about how 3I Atlas interacted with the solar wind and magnetic fields as it passed through. NASA's heliophysics division used these measurements to better understand how interstellar material behaves under the influence of the sun's charged particles. Because 3I Atlas entered at such a unique angle, it experienced varying levels of solar radiation pressure. Observing how its motion subtly shifted in response gave researchers real-time evidence of how fragile, icy bodies from other systems might survive or disintegrate when encountering the energetic environment of another star. This information could one day help plan missions to intercept such objects before they vanish into the cosmic dark dot. In many ways, the act of tracking 3I Atlas became a symbol of how far humanity's scientific reach had extended. Just a century ago, astronomers could only dream of mapping distant stars. Now, they were charting the flight of a visitor that had crossed interstellar space. It was as if the galaxy itself had opened a window, allowing us a brief look at what lies beyond. The precision of the tracking data, accurate down to fractions of an arcsecond, represented one of the greatest collaborations between human ingenuity and cosmic chance. Every measurement deepened our understanding of galactic mechanics, stellar evolution, and the shared material history of star systems. Through these investigations, NASA confirmed that 3I Atlas was indeed an interstellar traveler, its path a thread woven through the fabric of the Milky Way. The trajectory told a story of ejection, endurance, and arrival, a journey that began in the cold outskirts of a distant system and ended, briefly, under the watchful gaze of human telescopes. The data revealed not only the nature of its motion, but also the incredible resilience of objects born from the chaos of planetary formation, cast adrift through time and space, carrying the elemental echoes of other suns. When NASA's telescopes turned their gaze toward 3I Atlas, what they expected to see was the predictable behavior of a comet, a frozen visitor from the far reaches of interstellar space, slowly warming as it approached the sun, releasing jets of vapor and dust, forming the characteristic coma and tail that have fascinated astronomers for centuries. But what they actually witnessed defied expectations and deepened the mystery surrounding this interstellar object. Instead of merely brightening in the way a typical comet would, 3I Atlas began to disintegrate, breaking apart into smaller fragments long before reaching its closest point to the sun. This premature breakup puzzled scientists and forced them to reevaluate what they thought they knew about both the structure and composition of such alien visitors. The first hints of disintegration came when astronomers noticed something unusual about the object's light curve. Typically, as a comet nears the sun, it brightens predictably, following a well-modeled pattern that depends on how sunlight causes sublimation of surface ices. However, 3I Atlas brightened at an extraordinary rate, faster and more erratic than expected. It reached a magnitude of about +8, making it visible even in small telescopes, far earlier than models predicted. Then, almost without warning, its brightness began to fluctuate wildly. Within weeks, it dimmed dramatically, a clear sign that its structure was collapsing. Observers around the world confirmed that its once cohesive nucleus had fractured into several smaller pieces, each following its own faint trail through space. For NASA's team, this early disintegration was more than a curious observation, it was a scientific revelation. Comets are fragile by nature, often held together only by the weak gravitational bonds between loosely packed ice and dust. But 3I Atlas seemed to fall apart much earlier than a typical comet would, especially considering its relatively large distance from the sun when the breakup began. The event occurred while it was still beyond the orbit of Earth, where solar heating should have been moderate. This raised profound questions. Was the object composed of more volatile materials than expected? Was it structurally weaker because of its long interstellar journey? Or was something entirely different happening, something that defied our understanding of cometary physics? To answer these questions, NASA coordinated observations using instruments like the Hubble Space Telescope and the Pan-STARRS Array. High-resolution imaging revealed multiple distinct fragments, each surrounded by a faint halo of dust and gas. The separation speeds of these fragments were incredibly small, only a few meters per second, indicating that the breakup was not explosive, but rather a slow mechanical failure. This gentle disintegration suggested that 3I Atlas was held together by extremely weak cohesive forces, perhaps the result of billions of years of exposure to interstellar radiation, which could have altered its internal structure. Over such timescales, cosmic rays can penetrate an object's outer layers, creating microscopic fractures and chemically altering ices into more brittle forms. The chemical composition inferred from its spectra also hinted at an unusual mixture of materials. Unlike comets from our solar system, which typically show a combination of water ice, carbon dioxide, and ammonia, 3I Atlas displayed an enhanced presence of carbon-rich compounds and complex hydrocarbons. These materials, while common in the cold interstellar medium, are more volatile and less stable when heated by sunlight. NASA's researchers speculated that as the object neared the sun, These exotic compounds may have sublimated rapidly, destabilizing the fragile outer crust and triggering a cascading breakup from within. In essence, the comet's own chemistry might have led to its self-destruction. The disintegration also carried intriguing implications about its age and history. The surface of 3I Atlas had likely been exposed to cosmic radiation for millions, perhaps billions, of years, slowly accumulating a hardened crust that trapped volatile gases beneath. As sunlight began to penetrate deeper layers, these trapped gases would have expanded, building pressure until the surface cracked apart. This kind of outgassing-driven fragmentation is not uncommon for comets. But what made 3I Atlas unique was the timing. It happened so early, and so violently, that it left astronomers wondering if interstellar comets might be inherently more fragile than those native to our solar system, having drifted unprotected through the harsh environment of interstellar space. Such objects could develop internal weaknesses that make them prone to early disintegration when exposed to a star's heat. Another compelling theory emerged from NASA's computational models: rotational breakup. As 3I Atlas approached the Sun, uneven jets of sublimating gases might have acted like thrusters, gradually increasing its spin rate. If it rotated too quickly, centrifugal forces could have overcome its internal cohesion, tearing it apart. This spin-up mechanism has been observed in several solar system comets, such as 332Pi Kea Murakami, which shattered due to rotational stress. However, for 3I Atlas, the process seemed to occur under unique conditions. Its mass, density, and shape were all unknown, and these parameters directly affect how fast an object can spin before breaking apart. By modeling various scenarios, NASA scientists found that even a small change in outgassing direction could trigger instability in a body with such a delicate structure. The Hubble Space Telescope's detailed observations provided further insight into the disintegration sequence. Images taken weeks apart showed that the fragments were dispersing along a curved path consistent with the parent body's orbital motion. This meant that, although broken, 3I Atlas still retained the memory of its original trajectory. The largest fragment was estimated to be only a few dozen meters across, surrounded by a diffuse cloud of dust extending thousands of kilometers. These fragments, though faint, continued to release material as they drifted away from each other. For NASA researchers, this was like watching the slow unraveling of a cosmic fossil, a process that revealed the internal makeup of an object that had been sealed since before humanity existed. As the fragments continued to fade, spectroscopic data revealed something even more remarkable. The composition of the released gases indicated an abundance of carbon monoxide and methane, gases that form only under extremely cold conditions. This finding supported the idea that 3I Atlas originated from a region far from any star, perhaps an outer disk similar to our Oort cloud. Such an environment would preserve fragile ices that would never survive closer to a star. If so, this meant 3I Atlas was carrying the chemical fingerprint of a place beyond the frost line of another star system, an ancient, frozen remnant of cosmic history. Its breakup was tragic in one sense, but it also provided scientists with a once-in-a-lifetime opportunity to study the chemistry of interstellar material up close. The premature disintegration also forced NASA to rethink the nature of interstellar objects more broadly. Oumuamua, the first interstellar visitor, did not display a visible coma and remained intact, behaving more like a rocky asteroid. Borisov, the second, behaved like a traditional comet and survived its passage around the Sun. 3I Atlas, however, combined features of both its interstellar origin was clear, but its fragility was extreme. This diversity among interstellar visitors suggested that they are not a single class of objects, but rather a spectrum, each shaped by the unique history of its parent system. NASA's researchers propose that while some interstellar bodies may resemble rocky asteroids, others might be composed of ultra-volatile materials that make them inherently unstable when entering a new star's environment. The timing of its breakup also carried practical implications for future missions. NASA and other agencies have long discussed the possibility of sending a spacecraft to intercept an interstellar object, but the rapid disintegration of 3I Atlas underscored the difficulty of such endeavors. Planning an interception requires predicting the object's stability over time. Yet 3I Atlas demonstrated that such predictions can be uncertain. A target that looks stable 1 month might fragment the next, making mission design extremely challenging. However, even in its disintegration, 3I Atlas provided valuable data that could help refine models for how such missions should respond to unpredictable changes in target structure. Another remarkable aspect of the event was how it changed the way scientists interpret light curves of distant comets and interstellar bodies. Before 3I Atlas, erratic brightness variations were often dismissed as observational errors or temporary outgassing events. Afterward, astronomers became more cautious, realizing that such irregularities might signal deeper structural issues or fragmentation. The lessons learned from this event are now influencing how observatories monitor and interpret the behavior of new discoveries, especially those with unusual trajectories or compositions. For many scientists, the disintegration of 3I Atlas was also a philosophical reminder of the fragility of cosmic bodies and the impermanence of matter itself. Here was an object that had survived unimaginable timescales, traveling across light years of empty space, only to crumble apart within sight of humanity. Its demise was quiet, almost poetic, scattering dust that would continue drifting through the solar system long after the fragments faded from view. Those particles, tiny and ancient, now joined the interplanetary medium, becoming part of the same cosmic material that builds new planets, moons, and comets. In that sense, the breakup of 3I Atlas became more than just a scientific event, it was a symbolic one. It reminded scientists and the public alike that even in its destruction, the universe continues its cycle of renewal. The fragments of one world become the seeds of another. NASA's continued analysis of the data gathered during and after the breakup has offered an unprecedented window into how fragile interstellar materials behave under stellar influence. The discovery not only expanded humanity's understanding of what lies beyond, but also deepened the emotional connection we feel toward these distant, mysterious travelers that remind us how transient, yet magnificent, every encounter in the cosmos truly is. When NASA scientists finally pieced together the immense amount of data collected from telescopes across the globe, they realized that 3I Atlas was more than just another cosmic visitor, it was a messenger carrying the story of another star system written into its molecular and physical structure. This realization didn't happen overnight. It emerged from countless nights of observation, careful calibration, and tireless analysis, drawing upon every corner of NASA's research infrastructure. What began as a curiosity, a faint, fast-moving object spotted by the Atlas survey, soon became one of the most significant discoveries in the history of modern astronomy. The data gathered from its composition, motion, and light patterns revealed a tale that bridged interstellar chemistry, planetary formation, and the shared origins of matter across the Milky Way. The first step in NASA's analysis was understanding what 3I Atlas was made of. Spectroscopic readings, light broken into its component wavelengths, acted as a kind of fingerprint for the object's chemistry. Every element and molecule absorbs and emits light in a unique pattern, so by studying its reflected sunlight, scientists could identify the ingredients on and beneath its surface. The spectra obtained from the Hubble Space Telescope and ground-based observatories showed features that were both familiar and strange. Familiar, because they included water ice, carbon monoxide, and carbon dioxide, the same volatile compounds found in comets within our own solar system. Strange, because embedded within those signals were traces of complex organic molecules and exotic carbon chains rarely seen in local comets. These molecules suggested that 3I Atlas formed in an environment very different from the one surrounding our Sun. The presence of these organics, especially long-chain hydrocarbons, was among the most fascinating findings. Such molecules often form in extremely cold environments, far from the heat of any nearby star, where ices can accumulate and react under cosmic radiation. NASA's scientists theorize that 3I Atlas likely originated in the outer reaches of its parent star system, in a region similar to our Oort cloud or Kuiper belt. But there was a twist: the specific ratios of carbon-based molecules and nitrogen-bearing compounds didn't match the profiles seen in comets that formed around the Sun. This difference meant that its parent system had a distinct chemical makeup, possibly indicating a star with a different metallicity or age. In other words, 3I Atlas was a physical sample of a solar system built under different cosmic conditions, a piece of another world that drifted across the galaxy for eons. Before entering ours, NASA's next major breakthrough came from studying how the object interacted with sunlight. As 3I Atlas approached the inner solar system, it began to release gases and dust, creating a diffuse coma around its nucleus. The rate and composition of this outgassing were carefully measured by instruments like NEOWISE, which detected emissions in the infrared spectrum. These measurements allowed scientists to estimate the relative abundance of different volatiles and their release rates. Interestingly, the gas output of 3I Atlas was not consistent with typical solar system comets. It showed an unusually high ratio of carbon monoxide to water vapor, implying that it had formed under colder conditions where carbon monoxide could remain trapped within ice. This reinforced the idea that 3I Atlas originated much farther from its home star than any comet we know from our system. As the quiet hum of the universe continues beyond the reach of our instruments, the story of 3I Atlas stands as both a revelation and a reflection of our growing awareness of the cosmos. It reminded NASA and all of us that the universe is not a distant spectacle to be observed from afar, but an active and interconnected system of motion, matter, and mystery. Every time an object like 3I Atlas enters our solar system, it brings with it the history of another star, another origin, another fragment of cosmic evolution that has drifted across the vastness of space to meet us, however briefly. These encounters prove that interstellar space is not empty. It is alive with travelers, fragments of creation that carry the stories of countless other worlds. Through its study of 3I Atlas, NASA did more than identify a comet. It began to understand a pattern of galactic exchange that links us to regions of the Milky Way we have never seen. It deepened our knowledge of how planetary systems form, how they dissolve, and how their remnants journey across light years to share their chemical essence with others. It showed that exploration is not just about distance, but about perspective, the ability to recognize that even the smallest cosmic visitor can hold lessons larger than our imagination. The lessons from 3I Atlas have changed the direction of modern astronomy. They have inspired new missions, new technologies, and a new generation of scientists dedicated to unlocking the secrets of interstellar space. The discovery accelerated efforts to detect these objects earlier, to prepare spacecraft capable of intercepting them, and to understand what they can reveal about the origins of stars, planets, and possibly life itself. Each discovery expands the boundaries of our curiosity and reinforces the idea that humanity's destiny lies not in isolation within one solar system, but as part of a greater cosmic continuum. Perhaps the greatest gift of 3I Atlas is the reminder that wonder and science are not separate pursuits. They are two sides of the same human longing to know our place in the universe. It is the quiet awe of looking up at the night sky and realizing that something from another star once passed silently through our cosmic neighborhood, leaving behind a trace of itself and a challenge to keep searching. In the brief light of 3I Atlas, we glimpse the endless bridge between worlds, a pathway that connects every atom, every planet, and every civilization that has ever looked to the stars and asked the same question: what else is out there? Good night.